We can also find out the power dissipated, the power that is dissipated in as heat. So that can also be represented as PL, where L shows the loss, and it may be written as PL is actually equal to half of VL and I steric, where steric denotes the complex conjugate. So likewise, it can also be written as half I magnitude square RL, in fact, now, because VL is actually can be written as I RL. So this gives us this equation. Now we already knew the value of I magnitude, so we can plug in the value of I magnitude and we can find out the power dissipated in the antenna, the equation for that. So it is, now by plugging in, you can find out easily, it is Vg square into RL. This time it is RL because it is loss resistance, and the same in the denominator, which is Rg plus RL plus RR square plus Xg plus XA whole square multiplied with 2. So this equation actually shows the power dissipated in antenna, in fact, the power dissipated in antenna. So and the reactive and imaginary power can also be now, so let me write the reactive power that is imaginary, what is the spelling of it? Imaginary component of the complex power stored, the reactive power stored in antenna, in fact, in the near field, antenna near field. So what is that going to be? So this can be denoted as Px, for example. So this Px is actually equal to half of Vx. So please remember that we let me draw the circuit again in order to remind you that we had Vg, in fact. So we had Vg and then we had Zg, and then we had no transmission line, and then we had 3 components, in fact, and those 3 components were R, RL and XA, JXA, in fact, and the voltage associated over here was VR, the voltage over here was VL, the voltage over here was Vx, in fact. So yes, so here we can easily find out Px is equal to half Vx into I steric, and the same way we can say this is equal to half J I XA, yes, it can be written like that, into I steric, okay, so which gives us I magnitude square into XA, in fact. So Px is actually Px has this equation, and by putting the value of, okay, so Px has this equation. By just putting value of I magnitude, we can calculate we can find out the equation of reactive power stored in the antenna near field. So it is XA divided by 2, and the same thing, RG plus RG plus RL plus RR square plus J, and then it is XG plus XA square, in fact. So this is the equation for the energy stored in antenna near field, in fact. So what in fact we are doing is, let me summarize it. So the summary is that if you look at this circuit again, that we have in fact ZG, and then we had only ZA, okay. So and the generator has the voltage of VG. Now looking at this, where the current I is flowing through it, if you look at this, we can only achieve, because this point A and this point B actually shows the antenna terminals, in fact, from this side then antenna starts. So if you want to maximally transfer the power from the source to the load, where load in this case is actually what is my antenna, in fact. So if you want to transfer the maximum power from the source to the antenna, from the generator to the antenna, for that you need to have one condition, and that is the maximum power transfer theorem, in fact. And maximum power transfer theorem says that if Zg is actually equal to Za, then this shows the condition where the maximum power is going to get transferred. So while we were finding out the different powers, we in fact found 3 different powers. One was P radiated, okay, which we considered as PR, and then we found out the P dissipated, okay, and that was denoted as PL, and then we found out the equation for the energy stored, I mean the reactive power, the energy stored in the near field of the antenna, and we denoted it as Px. So we found the equations for these 3 powers, in fact, and now we are going towards